All right, folks, let's talk about gas exchange. So you already talked about Boyle's law, and Boyle's law was the pressure-volume relationship, the inverse relationship between pressure and volume. Now we're going to talk about a couple other laws here. The first one is Dalton's law. We'll hit Henry's law a little bit. So Dalton's law says this, that the total pressure of the gas is the sum of all the partial pressures. That's what Dalton says. Now, if you look at our atmosphere, our air, we're 78% nitrogen, and actually, what your book tells you is 78.6% nitrogen, and that's diatomic nitrogen. That's molecular nitrogen, not the atomic nitrogen, but the molecular diatomic nitrogen. We are 20.9% oxygen. We are 0. I think in the previous slide I told you 0.03. Your book's rounding up. It's your 0.04% CO2. And something I left out when I previously did this for you is I assumed dry air, or I was actually just working with dry air. And there's places on the planet where the air is drier than others. Obviously, the Sahara Desert or the Arizona deserts are drier than Miami Beach, Florida. But what we do is we estimate a water vapor. So pressure due to the gas, the gaseous water vapor. And that's about 0.5% water vapor. That changes. So we're just using a shot on the dartboard when we pick 0.5%. Now, having said that, now you can calculate the partial pressures because all I got to do to take the partial pressure of nitrogen is 0.786 times the total pressure. For oxygen, 0.209 times the total pressure. For water vapor, zero point 0.5 times the total pressure, etc., etc., etc. And here is a table giving you all the partial pressures. All right, so that's dry air inhaled. Okay, now uh, why are they using dry air when they have? Oh, I actually don't agree with that. Here's what they've done. This is dry air. They kind of ignored the 0.5% water vapor, but then they didn't ignore it when it got to the lungs. Because in the alveoli, and therefore the air you're exhaling, that's saturated air. That because we humidify our air when we breathe it in. So they did take into account that this is humidified air when you get into your lungs. And that's why the partial pressure of nitrogen in your alveolus is lower than the partial pressure of nitrogen that you're inhaling. Because as you humidify it in your superior, middle, and inferior meatuses, and as you humidify it in your trachea, you have a partial pressure of water you got to account for. So this is the partial pressure of nitrogen in your alveolus. This is the partial pressure of oxygen in your alveolus. This is the partial pressure of carbon dioxide in your alveolus. And this is the partial pressure of water in your alveolus. All right. So that's Dalton's law. The total pressure is a sum of all the partial pressures. Henry's law says this. A gas under pressure will go into, at a liquid interface, will go into solution until it hits equilibrium. So before I push this piston down, so when the piston was up here at the dotted line, there was less gas in this solution. But then what I did is I pushed the piston down, and it made the pressures of these gases go up. So more went into solution until it hit equilibrium. Now, having said that, uh, there's a solubility coefficient for every different solution. And these solubility coefficients have to be experimentally determined. That means it's not like we can look it up, but somebody at some point in time in their life experimentally determined that. And they're usually listed in books like the Handbook of Physics and Chemistry or the Handbook of Biochemistry and Molecular Biology. Things like solubility coefficients are always listed in there. But somebody had to experimentally determine it at some time. Now, having said that, the opposite is always true. If I take pressure off this gas, if I take pressure off this gas, then the gas will come out of solution until it heats equilibrium. And the classic example of that is opening your can of pop. Your can of soda pop is under pressure. When you open it, the gas, so you just alleviated the pressure. There's less pressure here now because you open it to the atmosphere. And the gas in the soda pop comes out of solution and it bubbles or fizzes, whatever you want to call it. So this is Henry's law. Now, why do we care about Henry's law in a bottle of soda pop? This is because in physiology, CO2 is relatively soluble. It's soluble in plasma. It's not highly soluble, by the way, but it's more soluble than oxygen and nitrogen. So oxygen and nitrogen has a low solubility in plasma. And this is all about Henry's law. It's supposed to be an L, not a T. So oxygen and nitrogen have low solubility. In other words, their solubility coefficients are low, whereas CO2 is soluble in plasma. All right, so that's Henry's law. That's the collage of Henry's law. So here you go. I already listed it for you. CO2 is soluble, oxygen and nitrogen are not. All right. Now, I need you to memorize these numbers. However, I wouldn't memorize from this picture because a picture I'm going to show you shows you why you have to memorize them, and you see the bigger reason why those numbers become important. So let's look at that. That's coming up. All right, so here's 5 reasons why we have efficient gas exchange. The number one reason we have efficient gas exchange is because the partial pressures are different. Where are they different? They're different between the alveolus and the blood. They're different between the blood and the tissue. So the reason why we have external respiration and internal respiration is because of different partial pressures. That's the biggest reason. There are some other minor reasons. Our respiratory membranes are thin, 0.5 micrometers, so the gases don't have to travel a long distance. They are gases and lipid soluble, so they can travel through the phospholipid bilayer of your plasma membranes. We generate a huge surface area for gas exchange. You remember when we said one alveolus was 250 micrometers across? Well, you could do the volume. You could do the surface area and volume of this. You know, volume equals 4/3 pi r cubed. I'm not doing it, by the way. And you could do the surface area of this alveolus, and then you can multiply it by millions of these alveoli because there's millions of them in the lungs. And you would see that the surface area of the lungs is just huge. So we have a huge surface area for gas exchange. And then lastly, it's not that it's not important. It is very important. But the last listed here is your cardiovascular and your respiratory systems are coordinated. Your cardiovascular and your respiratory systems are coordinated. And I think I told you this back in the heart chapter, or one of the chapters. There is no sense in breathing faster if you don't send blood to the lungs more. Why breathe faster? If you're not going to send more blood to the lungs, there is no sense in breathing faster. So we coordinate our heart rates and our respiratory rates. And this is another reason why gas exchange is highly efficient. This is just anatomy over here on the left, and on the right it shows you high PO2s in the alveolus, low PO2s in the pulmonary artery, pulmonary capillary really, we're in the capillaries really. Therefore, oxygen goes this way. It's showing you high PCO2s in the blood and low PCO2s in the lungs. Therefore, CO2 goes that way. All right, now let's look at some numbers. What do I mean by low PO2? It's 40. Well, what's the PO2 in my lungs? 100. 100 is greater than 40, so oxygen enters the blood. Oxygen enters the blood until you hit equilibrium, until it becomes 100. Okay, let's look at CO2. What do I mean by high PCO2? Well, it's 45. You can see my PCO2 right here is 45. By the way, this is millimeters of mercury. Well, what's the PCO2 in my lungs? 40. Right here, you can see it. Well, 45 is higher than 40. So CO2 enters my lungs and then it can be exhaled. How much CO2 enters my lungs? Until you hit equilibrium and you hit 40. All right. So that's how partial pressures drive the movement of these gases. And I would memorize the numbers. It's not because the numbers are extremely important. It's so you have an application. Instead of just saying high, low, you realize the application. And you realize there's a greater driving force for the movement of oxygen than there is for CO2. See how oxygen has a difference of 60 millimeters of mercury, but CO2 only has a difference of 5? So that's why it's probably important to memorize those numbers. Now, this is at the tissues. First thing I want to point out is notice my PO2 is no longer 100, it's 95. All right, you're going to say, well, what the heck? What the heck, Kiggins? It was 100 a second ago. Yeah. Well, these endothelial cells of your blood vessels use oxygen as well. So even in the arterial blood, as it's floating around, you have some oxygen use. In addition, oxygen binds to hemoglobin, and it's a small amount, like 1% is dissolved in your plasma, because it's poorly soluble in your plasma. So that PO2 of 100 that you had in your pulmonary vein, it's going to be a little bit of flux because of the dissociation curve of hemoglobin, because of the solubility of oxygen in plasma, because of usage by endothelial cells. There's a small amount of flux there. You'll notice the CO2 didn't fluctuate because no one's using it. It's really a waste product. It's not like the cells are using it. Okay, so let's look at the tissues. Here's my arterial blood approaching the tissue. Here's my arterial blood coming down approaching the tissue. Let's do oxygen first. In my arterial blood, my PO2 is 95. But in my tissue, my PO2 is only 40. What does that mean? Oxygen goes into my tissue. See, the higher pressure dominates. Now, in my arterial blood, my PCO2 is 40. But in my tissue, my PCO2 is 45. So, CO2 goes into my blood. And then this is the blood that's being returned to my lungs. If I go backwards, you can see that's the blood being returned to my lungs. PO2 of 40 and PCO2 of 45. This is the blood being returned to my lungs. PO2 of 40 and PCO2 of 45. Now what you're going to say is, well, Kiggins, it's got to go through the right atrium and right ventricle first. Yes, it does. But it's still being returned to my lungs. The fact that it goes through the right side of my heart before it goes to the lungs is really inconsequential when it comes to gas exchange. It's still being returned to my lungs. All right. So that's how we move gases, by these partial pressures. This is the collage. This is what I would look at and study a little bit. This is another graph. It's showing you the same darn thing, but it's graphically. I did not use these graphs on the test, but this is a graphical demonstration of what we just talked about. And the numbers are the same, by the way.
Respiration serves as a means for the body to exchange gases with the atmosphere via the blood. The partial pressure of oxygen, PO2, in the air in the alveolar spaces in the lungs is greater than the PO2 in the blood, so oxygen diffuses into red blood cells from air in the lungs. Also, the partial pressure of carbon dioxide, PCO2, in the air in the lungs is less than the PCO2 in the blood. So carbon dioxide diffuses out from red blood cells and into the air in the lungs. Oxygen-rich blood is carried through pulmonary veins to the heart and then pumped through systemic arteries to the body. The PO2 in the blood is higher than the PO2 in the body tissues, so oxygen diffuses out from red blood cells at the body tissues. Also, the PCO2 in the blood is lower than the PCO2 in the body tissues, so carbon dioxide diffuses into red blood cells there. Oxygen-poor blood is carried through systemic veins back to the heart and is pumped through pulmonary arteries to the lungs, where gas exchange again replenishes the blood with oxygen and removes carbon dioxide. Fresh air entering the lungs carries oxygen to the alveoli. The amount of gas in air or of gas dissolved in a fluid can be expressed as partial pressure, which is measured in millimeters of mercury. The partial pressure of oxygen in the air within the alveoli is 104 millimeters of mercury. Carbon dioxide that enters the alveoli from the blood causes the carbon dioxide concentration in the air of the alveoli to be 40 millimeters of mercury. Carbon dioxide is continually removed from the alveoli as air is expired. Blood coming from the heart at the arterial ends of the pulmonary capillaries has a partial pressure of oxygen, or PO2, of 40 and a PCO2 of 45. Therefore, oxygen diffuses from the air in the alveoli into the blood, and carbon dioxide diffuses from the blood into the alveoli because of these differences in partial pressures. Oxygen and carbon dioxide diffuse until there is no difference in partial pressure in the air and the blood. At this point, there is no more net movement of O2 or CO2. Therefore, at the venous ends of the pulmonary capillaries, the PO2 in the blood and alveoli is 104, and the PCO2 in the blood and alveoli is 40. Some oxygen was removed from the blood to nourish lung tissue. Therefore, the PO2 in arterial blood leaving the heart is 95. Oxygen diffuses out of the arterial ends of tissue capillaries into the tissue fluid, then into the cells, and carbon dioxide diffuses out of the cells into the tissue fluid, then into the blood because of differences in partial pressures. At the venous ends of tissue capillaries, the PO2 in the blood is equal to the PO2 in the tissue fluid, and the PCO2 in the blood is equal to the PCO2 in the tissue fluid, resulting in no more net movement of O2 or CO2. The blood now carries the O2 and CO2 to the lungs. In the body, all of these exchanges occur simultaneously.
Okay, that's gas exchange at both ends, at the tissues and the lungs. See you next section.